So in this video, we will discuss the that the connection between the differential cross section uh, in the lab and center of mass frame. And we know that the number of the scattered particle during this scattering, that number of the scattered particle cross section is independent of the frame. That number of scattered particle, they are same in the lab frame as well as the in the center of mass frame, and we can denote this cross section with the t omega, this infinitesimal cross section by this, and we can say that this is the same in both frame of reference. So this is represent the cross section in the lab frame, and this is representing the cross section in the center of mass frame. So they are both are same, they are independent of the frame of reference, you can say. uh, and the solid angle, which we denote with the d omega, is different in the frame lab as well as in the center of mass frame in the scattering problem. And we can write the expression for this is the solid angle in the laboratory frame. So that is sine theta 1 and d theta 1 and d phi 1. So theta 1 and phi 1 are the polar angle. This is scattering angle for the particle, and this is I'm writing the expression for the uh, incident particle, scattered incident particle, scattered incident particle that earlier we denoted with us m1, m1 particle scattered, and that is scattered through this element uh, or through angle, this solid angle d omega. We can write this expression sine theta 1, and similarly in the center of mass frame we can write the expression for solid angle sine theta d phi in the center of mass frame. So here these both are same, independent of the frame of reference. If I multiply this with this term d omega and divide with the d omega, so here I'm multiplying and divide with the same term, so this is 1. If I multiply with 1, it doesn't affect my result. And here this side, right hand side, I also multiply and divide with the d omega, so this is also 1, so it doesn't affect this relation. So if I rewrite in this fashion, so this quantity is well, representing the differential cross section, and this is in the lab frame, and this is represent the differential cross section in the center of mass frame. So we got this relation. So on rearranging this, we can write that this is scattering cross section, differential cross section in the lab frame, which is equal to this. And by substituting the value of this solid angle in the lab frame and center of mass frame, we can substitute here. So we will got this type of relation. So here now we will can uh, in this fashion. And another thing here, we will consider that in this scattering problem. Another thing is here, there is cylindrical symmetry around the direction of incident particle. It means that this azimuthal angle, that angle is phi, is independent of the frame, that it is same, phi is equal to phi 1 is same in both frame of references. So from here, if I say that the azimuthal angle is same, then we can say that this d phi is equal to d phi 1, and here we can, they will get cancelled, and finally you will get this relation. So here uh, we got the this type of expression here for the differential scattering cross section, and we can rewrite this in term of this d cos theta on d cos theta 2 cos theta d theta 1. So how I can rewrite this, because I know if I take the derivative of this d cos theta d theta, this is equal to sine theta. We know this is derivative, and I can rewrite this d cos of theta is equal to I have taken the derivative d theta of cos of theta. So I know this is equal to cos theta. This I rewrite, I can write this sine theta d cos of theta. Similarly, for the here is sine theta 1. So d theta 1 uh, cos theta 1. So its derivative is sine theta 1. I think it is with negative sign. So this is minus uh, positive negative sign doesn't affect here because here we will have these ratios, so that will get cancelled. So this is sine theta 1. So I can rewrite this d cos of theta 1 is equal to sine theta 1 d theta 1. So if I can write this sine theta from here, sine theta, no, no, here d cos of uh, theta 1. No, no, this is d theta 1 and this is d theta here. This is d theta. Okay, I'm wrong here. So on rearranging this, I can write this d cos of theta is equal to sine theta d theta. So I can replace this sine theta d theta with the d cos theta here. And in similar fashion here, d cos theta 1 by d theta 1. This, if I take the differentiation, this comes out to be sine theta. Okay, I will not take care of plus minus sign this because here we are taking ratio, then they will get cancelled. Okay, so here from here this d of theta 1 is equal to comes out to be sine theta 1 d theta 1. So instead of this I can write uh, this quantity. Mm, this is d cos theta 1 which is equivalent to sine theta 1 d theta 1. So I can replace with this quantity, and here uh, d cos theta is equal to sine theta d theta. We can replace it with the d cos theta. So here we got this type of action. So here we have to, why we do this, because in the earlier lecture drive the connection formula for the scattering of the target particle, uh, how they are connecting uh, with one another in the lab frame, and how the scattering angle is connecting in lab and center of mass frame. So that formulas we have earlier derived, and those formulas, what was that formula? We have derived connection formula, that this is for the particle M1, and in particle M1 incident particles. So that is the relation with this. Theta 1 is the scattering angle in the lab frame, and theta was the angle in the center of mass frame. So earlier we have derived this relation. In the one of the lecture, video lecture, I have explained this. So this is the relation between the scattering angles in the lab and center of mass frame for the particle M1, and that is the scattered incident particle through an angle, or you can say that theta 1. So this, we got this expression. So now we know that here in this relation, we uh, uh, theta 1 uh, this, and we know that uh, we will differentiate it with respect to now theta 1, because we know that in the our relation here we have to solve this. Here is d cos theta divided by d cos theta 1. So we know this cos theta 1 relation, that is given by this. So we rewrite in the reciprocal manner d cos theta 1. We have to find this parameter. Okay, so what we will do, that we know that cos theta 1, so we will take the reciprocal of this, so that d cos theta 1 divided by d cos theta, and we will differentiate, you can say, with respect to cos theta. So this we have to differentiate it with respect to cos theta 1, this relation. So this is cos theta 1 in the bracket, within bracket, and now we have to differentiate. So we will make the simple differentiation in this case now. So in this simple differentiation that I have solved it here. So if we solve here, you know that there is a square root, and this is comes out to be square, so under root term will be vanish here. And now in the denominator, in this above, what we'll do now, that we will write as it is this term 1 plus this term, and derivative of this term. Now derivative of this term with respect to theta is 1, and this is constant, so this is 0. So this is 1 plus 0, and with now negative sign, with minus sign, differentiation of this, it comes out to 1 by 2, and derivative of this term uh, is 2m1 by m, and this is differentiation of this cos theta comes out to be 1, and we have to multiply with this term. This is uh, minus 1 minus half, half minus 1 by 2, so we'll get here 1 plus this, and power raised to power minus 1 by 2, and we have to multiply it with this term as it is. Okay, this is simple uh, differentiation. So on solving it, so if I rewrite this expression, because here this is, you can say, this term, we can write this whole term divided by, because here minus 1 by 2. So if I take it in denominator, so this term comes out to be 1 plus half, because here this is minus sign, and we have to multiply this under root term with this. So this we will get here 1 plus m1 square, m2 square, and 2m1. So you can simply simplify this, you will get this type of expression here, as it is square root with term will get cancelled. And on solving this, uh, this term, uh, 2m1 cos theta divided by m2, and this m1 I m2 cos theta 2, and both are the same term. So we left with here, this is twice of this, we get here m1 by m2 cos theta, and this we on multiplying this m1 square by m2 square. Okay, and in denominator we get this. Okay, and here these both terms, they are same, so they will get cancelled. You can cancel here, and we left with here 1 plus m1 by m2 cos theta, and this term. So we got to finally this expression here for the differentiation with respect to theta. So we got this is the differentiation. So that this is d cos theta, because we have to use this relation here. Yes, we have to substitute the value of this. So from here, because this is basically, we have derived the, this is equal to d cos theta 1, this is d cos theta 1 d cos theta. So here in this relation, we have to substitute the value of d cos theta. So we have to take the reciprocal of this quantity in this expression. So on substituting here, you will get this is the value of d cos theta 1. Okay, so this is value, and we substitute in the cross section term, differential cross section, a relation here, the value of this. So we got this type of relation. So this is a relation representing the uh, differential cross section connection formula for the particle m1. This is for the m1 particle, and that is the related to the target, not target but incident scattered particle. So in the similar fashion, you can find out the uh, uh, this type of a relation for the scattered target particle, which we earlier denoted with the m2. And for that relation, we can write in the similar fashion. Here we will also write this is dn d sigma theta phi 1, this is equal to d sigma theta phi. This is in the cm frame, center of mass frame, and this is for the lab frame, and they are same in both frame. So here we have to multiply and divide it with the d omega 2. This side we have to multiply d omega 2, and here we have to multiply, divide center of mass frame with d omega, and we wrote here d omega 2 relation for the d omega 2 is in the lab frame, that is sine theta 2 d theta 2 d phi 2, and similarly d omega is equal to sine theta d theta d phi. And again here by due to the cylindrical symmetry around the incident uh, uh, due to cylindrical symmetry around the direction of incident beam, we can say that azimuthal angle phi is 1 is equal to phi, or here d phi 1 is equal to d phi. So by simply we get in simple fashion this, and we know that earlier we have derived the relation for the this angle uh, cos of cos of 2 theta, that is connecting a relation that we drive in term of, I think, in tan tangent uh, theta 2 is equal to cot theta by 2. No, cotangent theta by using this relation here in this we on substituting here, finally we get this type of a relation, and this relation is representing the connection formula, or connecting the lab and scattering cross differential cross section for the particle m2, scattered particle m2. So in this fashion we can uh, drive the connecting formulas. Thank you.